we now, as the next ingredient, we define something that was called the Yell function. The Yell function is a function, a scalar function of the stress and the hardening variable, alpha. So it was defined for U-unity cases in that way. The modulus of the stress minus the Yell function, which was given by the hardening softening law. And then we define the following. The Yell stress, so in any space, typically in a space sigma alpha, only the positive part of this space, because alpha is always greater than 0, we define that every admissible points were those in which f of sigma alpha is smaller than 0, so the modulus of the stress is smaller than the Yell function. That means that typically for a given value of alpha, all these value of stresses are attainable, and the space at which these stresses can take is what is called the elastic domain. The elastic domain is that the value of the stresses such that f of sigma alpha, Yell function, is strictly smaller than 0. So it's all those possible values of stresses. You look at the elastic domain grows as alpha grows according to that. So as the sigma, the Yell stress increases, the size of the elastic domain increases. And then the limit, the border, the external boundary of this domain, which are this point and that point, so the points where the Yell stress is strictly equal to 0, so where sigma is exactly sigma the Yell stress, defines what we call the elasto-plastic domain, or the Yell surface. So the Yell surface is then defined as the boundary. That's an important concept because it will be extended for three-dimensional cases. We have the elastic domain, so the points that where the material interior to this the Yell function defined by this inequality, the Yell function, and the boundary of that is what is called the Yell surface. In 1D, the Yell surface is just made by 2 points, the boundaries of this interval, right? And at those points, the Yell function is strictly equal to 0. So next point is, okay, what happened with points where the Yell function is greater than 0? Look, here is smaller, here is equal. What about if it's greater? So what about those points here? Well, that's important. We assume that these points are not reachable, are not attainable. So f of sigma alpha greater than 0 is assumed impossible. That's part of our model. And you will see that this helps us to define or to replicate, to mimic the phenomenological model that we observe in experiments. So that's the Yell function, which is a sort of test that allows defining what is given a given stress state and an internal variable, a Yell hardening variable value alpha. We can check if f of sigma as alpha is smaller than 0. That means that we are in elastic state, and then we can take decisions about that. If we check that this is strictly equal to 0, we are into an elastic plastic state. That is, in this domain, we are at the boundary, and then we'll take some decisions according to that. And f of sigma alpha greater than 0, it's assumed that it never can be taken. So, in other words, as one point tends to increase, to exceed those limits, what happens, and we are going to make alpha grow so that this stress state goes to the boundary. Okay? I'm anticipating what is happening. So this is what the role, the aseptic role of the Yell function. Okay. So as I told you, that is defines the space of admissible stresses. So the space is the sum of the elastic domain, so the elastic space, so all the possible elastic domains then can be achieved in terms of the evolution of the hardening variable alpha, define the elastic domain, and the boundaries define what is called the adherence of this domain and the union of this elastic domain plus the adherence define the admissible stresses. Why admissible? Because, as I said, we postulate that we can, for a given value of alpha, we can never exceed this value. If we want to exceed this value, there is only the possibility of increasing alpha so as to sigma finds a value for alpha and which it's at the boundary at the corresponding Yale surface. Okay? So, recalling that we define the Yale function determined in terms of the value of this Yale function, an elastic domain, and the boundary of this elastic domain, which is the Yale surface, and both configure something which is the admissible stress space, the admissible stress space, in that sense that out of that there is no life, there is no possibility unless we just produce a variation of the hardening variable. Okay, so now we can take decisions about that. Now we postulate the following. If we are in the elastic regime, so if sigma belongs to the elastic domain, that is, in other words, if f of sigma alpha, as I would say, f of sigma alpha is smaller, strictly smaller than 0, then we postulate that the behavior incrementally is elastic. So the increment of the stresses and increment of the strains are related to the Young modulus if the material was elastic. What is that? Look, in this diagram, this represents that we are either in one point like that or in one point like that in the unloading branches, elastic branches. So then incrementally, both increasing the strains or decreasing the strains, there is complete reversibility. The behavior is purely elastic. Incrementally, the only difference is that incrementally, every increment of stresses corresponds to the increment of strains whenever we are at the interior of these branches. Okay? Well, the other possibility is that we are just at the boundary, at the Yale surface. In that sense, now we have to distinguish both cases. So, if we, by some reason, we are at the boundary, but now next step takes the stresses at the interior, so the Yale function is 0, but the increment of the Yale function is smaller than 0, which means that then the stress tends to enter into the elastic domain. If that is the case, we call unloading. This corresponds to this situation. We are right here, just on the limit, just on the plastic branch, elasto-plastic branch. But now the evolution of the problem takes the stress to decrease. The Yale function, then the increment of the Yale function is smaller than 0. And that means that the point is going to become elastic. It's going to enter into the elastic domain. So it's what we call unloading. So that's what physically or graphically in that plot is that we are just here, but now we unload. We are moving, but decreasing the stresses. We are entering into the elastic domain. That is what we call unloading. And what is the behavior there? Exactly, incrementally elasto-plastic, the same here. But it could happen that being here, there is a trend of the problem so that the stresses tend to increase. In other words, that differential of sigma alpha is equal to 0. Well, equal to 0 means that if we are at the boundary, the point remains at the boundary. What is that? So differential of phi is equal to 0, of f equal to 0, so means that if f equal to 0 and the increment of f is equal to 0, that means that the point is remaining in the elastic, in the admissible domain. But how? It moves that way. That's what we call loading. So we are here, and the point tends to move in that branch. So that means that f being f0, f remains 0. Then the situation So then the stress belongs at the boundary of the admissible domain, so remains on the L surface. Then the increment is another one. The increment of the stresses are equal to this slope that we are going to compute, EEP times the increment of epsilon. And look, if sigma is at the boundary, why not differential of S? So we have checked sigma being at the boundary here, unloading, so differential of F, increment of F smaller than 0, that is elastic, so it moves towards this branch. Sigma is at the boundary, but then differential of F, increment of F is equal to 0, so sigma remains on the plastic branch. And the point is, why not increment of F is greater than 0? Increment of F is not greater than 0 because if sigma belongs to the boundary, so F is equal to 0, and increment of F is, differential of F is greater than 0, that means that F would become greater than 0. And that's impossible. I have postulated that F is also smaller or equal than 0. So this never happens, okay? So then the only possible situations is either we are at the elastic domain in one of these branches, the incremental constitutive equation is elastic. If the point is at the boundary, so at the elasto-plastic branch, now we have to distinguish unloading. Unloading meaning that the increment of F is smaller than 0, and then the incrementally unloading behavior follows the slope of the elastic branch. And then the other possibility is that being F equal to 0, the increment of F is also equal to 0. So F being on the L surface, the point remains on the L surface. And then the increment of stress is no longer ruled by this slope, but is ruled by this slope, which is called the elasto-plastic tangent modulus. Is that a material property? No. You will see that this is something that we can compute in terms of the other properties that we have defined so far. I recall that we have defined so far as properties the Young modulus, the elastic limit, and the hardening modulus H prime, okay? Okay, but this is now the constitutive equation. So for all possible situations, we know now how it's going to be the variation of the stresses. Variation, which is typically elastic in the elastic branches. Elastic if we are at the L surface but in unloading, so tending to move back, to move to the interior of the elastic domain, and then in the behavior we postulate it's incrementally elastic, and then when the point is at the L surface but it tends to remain on the L surface, can never go out, then we postulate a different relationship, incremental relationship, stress sustained, in terms of this elasto-plastic tangent modulus. And that's it. That's it. So now, look, we are mimicking the behavior that we have observed in the uniaxial tests. So the material can load and unload reversible in a reversible manner in the elastic branches. As the material goes to the elasto-plastic branch, if it grows, it moves on the branch, then it increases according to this slope, and if it decreases the stress, then it decreases it according to this law, so to the elastic modulus slope. And that's it. What remains now to compute this value here, elasto-plastic modulus? Let's see.